So last video, we introduced the quantum harmonic oscillator, right? Which was essentially a system that's very common and used a lot in quantum mechanics and physics. But the gist was we have the Hamiltonian of a quantum harmonic oscillator is p squared over 2m plus 1 half m omega squared sat squared, right? What we did last time is we were able to recast this Hamiltonian as h bar omega a dagger a plus 1 half, where, or written even another way, h bar omega times the number operator plus 1 half, where we had defined our raising operator a dagger as m omega over 2 h bar all square rooted times x hat minus I, the momentum operator, over m omega, and our lowering operator m omega over 2 h bar square root x hat plus I p hat over m omega. And obviously the that number operator was defined as just a dagger a. And what we did is we used these things and we developed this sort of new operator method of solving our energy eigenvalue equation. Our H n is equal to En times n. That energy eigenvalue equation, we derived essentially that whole spectrum using just the commutation relations. And what we ended up showing was that we derived those energy eigenvalues to be h bar omega n plus 1 half, right? And when all is said and done, started using this really powerful technique, using just those raising and lowering operators, solved for what the spectrum was. We saw where this raising operator and lowering operators got their names from, because essentially we have this ladder of energy states, starting with the 0 point energy at the bottom, and the raising operator takes us to a state that is increased by 1 h bar omega of energy, and we can go up or down this ladder of states using those raising or lowering operators, also known as ladder operators for that reason. So we're, one of the sort of goals is to solve this energy eigenvalue equation, determine what the spectrum is as well as the energy eigenstates. Last video, we determined what the energy eigenvalues were. In today's video, we're going to focus on how can we determine what these energy eigenstates are. And we're going to use, we're going to keep going with this operator technique we use. We could just take our Hamiltonian and put that in the position representation and solve that, which would essentially just be negative h bar squared over 2m, the second derivative with respect to position of our energy eigenfunction, plus 1 half m omega squared x squared. That energy eigenfunction would be equal to our energy eigenvalue times that energy eigenfunction. This is a big differential equation. We could attempt solving that. We'd probably, go through a power series expansion or solution and get that. We would get the exact same results that we're going to get today. There's several textbooks and probably online resources that can walk you through solving that differential equation if you want to look into it. Today, what we're going to do is continue with our operator method and solve those eigenstates using that. To do this, we're going to use the same ladder termination condition we used when we were looking at the eigen spectrum, the eigenvalues of this, where we have some n lowest, which, let's just be real here, we already solved for this. If we take our lowering operator and act on that bottom state, that 0 state, we get zero, right? There is some lowest state, the n equals zero state, and if we try to take the ladder operator and operate on that lower, we get zero. We can take this equation, our ladder termination equation, and we can do that in the position representation, which would just be, that A operator acting on our zero eigenfunction equals zero. And we know our A operator, our lowering operator, is just m omega over 2 h bar square rooted times x plus I p over m omega, acting on that zero eigenstate or eigenfunction equals zero. And knowing that knowing what our position and momentum operators are in position space, this gives us a differential equation, but a much simpler one than what we had if we were trying to solve the full general Hamiltonian. So in this, we've used that, our momentum operator is negative I h bar ddx, and our position operator is just x. So, oops, this should actually be plus because negative I times I gives us positive. If we do that, we end up with a differential equation. If we bring things to the opposite sides in that, we have the second derivative of our ground state energy eigenfunction. Sorry, the first derivative of our ground state energy eigenfunction is just negative m omega over h bar x phi naught of x, right? Which is a simpler differential equation. We can solve this essentially by inspection, right? So by inspection, we know that, we can have this is going to be proportional to some exponential function, negative alpha x, something like that, perhaps. If we take the derivative of this, we'll get the negative sign out, but we also need, this x out in front. So if we square that, right, and we get our first derivative, this gives us negative 2 alpha x times a e to the negative alpha x squared. This is just our initial phi naught. So the first derivative of our sort of test inspection function, negative 2 alpha x times our test function, which looks really similar to this. If we define, we need our 2 alpha to be equal to m omega h bar for these to be the same, or our alpha to be equal to m omega over 2 h bar, right? And if we get that, then we have a function that matches our differential equation. So we've essentially shown that our ground state, or zeroth order, or not zeroth order, our n equals 0 wave function is equal to some constant e to the negative m omega over 2 h bar times x squared. And if we were to normalize that, integrate the probability density over all space, that has to be equal to 1. If we go through all that process, it's going to give us that our A is equal to m omega over pi h bar to the 1/4, right? So again, just looking at that ladder termination condition, we got a much more straightforward differential equation that gives us our ground state wave function is equal to m omega over pi h bar to the 1/4 e to the negative m omega over 2 h bar x squared. And that is our ground state wave function for our simple harmonic oscillator, our quantum harmonic oscillator. To figure out the rest of these, the wave functions, we are just going to, we just take the raising operator and act on this, right? We know that the raising operator acting on our zero state is going to give us something proportional to the first excited state, or the n equals 1 state. And likewise, then if we were to act on that state, we'd get something proportional to the n equals 2 state, and so on and so forth. And we can just take this raising operator and act on all of these states and get our the full spectrum of wave functions. But we have to be careful. This is only proportional to, right? So we need to determine what that proportionality constant is in this case, because we know these raising and lowering operators do not preserve normalization. So we have to be careful about this. The way we're going to do that, so if we look at, the raising operator acting on some state n is going to equal some proportionality constant that corrects this normalization times the n plus 1 state. And likewise, the lowering operator acting on that is going to give some other constant times the n minus 1 state. And we'll call this plus and minus. So let's look at and determine one of these constants. Normalization basically means that the magnitude squared of that state has to be equal to 1, right? So that magnitude squared is just going to be the complex conjugate, or the Hermitian conjugate of that vector, the bra of it, times the vector itself, which is just equal to n a dagger a on n. But this operator, a dagger n, if you recall, we defined a number operator that was equal to a dagger n, and it had the eigenvalue equation where it just gave us the n of whatever state we were in. So this ends up being equal to n. And so if we take the lowering operator acting on that n state, we end up with just getting n, right? And this should also be equal to, we did it from this side of the equation, but we should get the same thing from that side of the equation, is just going to be that that sort of normalization constant squared. So for our lowering operator acting on an n, to get the normalized state of what that produces, it's going to be just square root of n and the n minus 1 state, right? So that gives us sort of the action of the lowering operator on an energy eigenstate. And we can do the same thing for the raising operator acting on an energy eigenstate. I'm going to give this as a homework, I think, but it essentially gives us the n plus 1 energy eigenstate with this sort of normalization term there. So we can use these to derive the rest of our spectrum, because we have, again, we know our ground state wave function, we solved that above. If we act on that with our raising operator, we're going to essentially get this n plus 1 times the next excited wave function, which means our n equals 1 state is just going to be a dagger over root n plus 1, n being 0. So this is just root 1, phi times 0 on x. And we know the position representation of that raising operator, so we're set. And then we just keep doing this for subsequent levels, right? If we wanted the phi 2 state, the n equals 2 state, it would be a dagger over the square root of 2, because it would be 1 plus 1, times acting on the first state, and so on and so forth. And essentially what this brings up, if in general, if we want the nth state wave function, it's going to be 1 over the square root of n factorial, because we're going to, this n plus 1, n is going to keep coming out, times a dagger to the n times phi of 0 of x. You can sort of see this little recursion relation where if I plug this into here, I'm going to have the 2 times 1 in the square root here. That gives me this n factorial. I'm going to have the a dagger is going to be there twice, so it's a dagger squared now, and so on. So this sort of gives us our general way of getting a general wave function, or we want to write it one more way in the position representation, 1 over square root n factorial times our raising operator, which is m omega over 2 h bar square rooted x hat minus h bar over m omega d dx to the n times our ground state wave function. This is actually should just be x. And we can use this to get our differential equation to solve for whatever state we want, n equals 1, n equals 2, and whatever. It's not a very pragmatic approach, right? With the momentum operator in here having this derivative, we end up having to take an nth order, an nth derivative of this ground state wave function. So, if say you wanted the n equals 10 state, that becomes very sort of tedious and not very efficient to do. But it turns out what you end up getting is, if you look at the form of our ground state wave function way up here, every time you take a derivative, you're going to multiply an x down here. And then the next time you do a derivative, there's going to be a chain rule. So what you end up with is an exponential times a polynomial to the nth order, right? And those polynomials, turns out they have a name. They're called the Hermite polynomials. Hermite polynomials. And, we'll give them the symbol h, and we'll use that variable. And in terms of the Hermite polynomials, this has a general sort of solution where our nth eigenfunction is equal to m omega over pi h bar to the 1/4 times 1 over 2 to the n factorial times the nth Hermite polynomial, that times e to the negative eta squared over 2, where we've defined this variable here is a dimensionless variable that is m omega over h bar all square rooted times x, right? So we do substitute that variable in, and this is we've sort of arrived at our wave functions for our harmonic oscillator. In terms of what those Hermite polynomials are, so the 0th order one's just 1, the first one is 2 eta, and so on and so forth. So these are listed in the textbook. What do these wave functions look like in our harmonic oscillator? Well, they look like, let me blow that up a bit. They look like this, right? When we take in, well, not the Hermite polynomials. These are the whole wave functions in our harmonic oscillator. It's the ground state one's just that Gaussian type function with a single antinode in the well. Our n equals 1 has 2 antinodes within the well. They're oscillatory in the well. They do come outside and have some wave function penetration into what would be the classically forbidden region. As we increase in energy, we get more curvature. All those properties that we discussed in 323 and in the first semester of quantum, we see that in these wave functions. So a lot of the things we would expect, just qualitatively, we see in this. But now we have the actual functional form of these states. And if we look at the probability densities of these, again, you just square those wave functions and we get these. where again the amplitude's increasing as we go towards the turning points. Likewise, the wavelength slightly changes. Anyway, so we've derived our wave functions now and our full, so we know our full energy spectrum as well as the eigenfunctions that are associated with them for our harmonic oscillator. Um, we're going to keep working with this for another video or two. If you have any questions, please email me or bring them up in our synchronous sessions, and hopefully we can really start to work with these and get a better handle on understanding them. I will see you in the synchronous sessions.